So you have a bunch of keys and a bunch of doors, and in the input it specifies for each key which set of doors they can open. And the problem is to go through all the doors. So like we can label these doors in the order you come across them, like 1, 2, 3. So these are like the doors that you have to open with the key. And for each door, we want to assign it a key so that we can open that door. And the rules are, for each key we can only use it once. So for each key we can only match it to one door. And so yeah, the problem more precisely asks how many doors can you go through if you go through them in this order. So how many doors can you match, starting from here and going down. So yeah, the rule is each key can be used at most once, and also each door is going to end up having exactly one key to it. And so that means we're going to have a matching between the keys and the doors. And so in the matching, the pairings of keys and doors we're allowed to use, as I said, are specified in the input. So each key can open some subset of doors. So we can represent this as like the first key can open like door 1 and door 2. Second key can open door 1. That's probably not good. So the third key can open nothing. I'm not sure if that's possible or whatever. And the fourth key can stay open all 3.
What if the doors just unlock? Like there's a room which is you get a key from that.
Yep. So I guess these are the locked doors.
Yeah.
The rest of the rooms, it doesn't really.
Oh right, you just go for them. Yeah.
Yep. So pretty much considering how many locked doors we can get through. Yeah, so are we kind of happy with the fact that we're trying to create a matching between keys and doors? So each key will have one door, each door will have one key.
Yeah. But it depends on the order you get the keys, right? So like, say you don't get the fourth key until you get into like a room past the third door. You won't be able to use the third door to unlock these 3 unlocked doors.
Yeah, that's right.
Oh, I guess you'd only connect it to like doors which come after it.
Yeah. Yeah, that was kind of a nuance of it. So
yeah.
we only connect keys to like doors, like in the list of keys that we have, we only connect it to the doors that appear like in the rooms after the room where the key appeared.
Yeah, okay.
I'm not sure if it's hard to see at all, but it turns out that that's enough. Like you can't do anything invalid if you just respect that.
Yeah, yeah.
Okay, cool. So I think we're happy that we've reduced this problem to, we have this graph and we want to match as many of these to something on the left as possible. And if we just want to see if we can match all of these doors to a key, this is a pretty common problem, which is just maximum matching in a bipartite graph. And that literally answers how many of these can we match. So if we're just trying to maximize how many of these we can match. In this case, what would it be? In this case, I think it would be 3 because you can take that edge. Take that edge, and that edge. And this matches every door. And so in this case, the maximum matching is size 3. So one idea for a solution which works is to just see if there's a matching, only considering this node. So a matching considering this node and all the keys. And then these 2 nodes representing doors, and if there's a matching there. And you keep going until there's no matching, at which point that's as far as you can go. So that should be a working solution. Time complexity is, in the worst case, it's like something probably a bit too big, but it turns out like bipartite matching, it's pretty hard to find a worst case. So if you just do that, you're probably fast. That's my best guess.
I think the time complexity was V root V or V root E, something. E root V or something along those lines, if you use Dinnick's algorithm on bipartite matching.
Yeah. I forget the bounds of the problem, but in that case, is it fast enough? If you do it V times? as well.
You can also do it in less than v times if you do
Yep.
binary search.
Oh.
Right?
On the answer.
Yeah, you could do that, I guess. You could binary search to see to see the longest prefix you can match.
Yeah.
But the best thing you can do is know the algorithm, which I haven't explained.
Yeah.
But how the algorithm works is it actually considers each node one at a time. And so it will take the first node, it will match it to something. That's pretty simple.
Okay.
The second node, it will consider the second node, and it will find some. If it can, it will find something to pair it to. It might change other parts of the graph, but it finds something to pair it to. So there's a valid matching on these two if there is one. And so it keeps going through and adding a node if it can. And if it can't add a node, then it will tell you, and so you know at that point you can stop and return the answer.
I might be misunderstanding what you mean by maximum bipartite matching, but if you delete all the edges coming into locked door number one, it seems to me that the maximum matching has more than one edge in it, but the number of doors you can reach if you can't unlock the first locked door is 0, right?
So are you saying if we just consider the first door?
If you make the integrity of the first door 0, by deleting those 3 edges that come into it, you now can't unlock the first locked door. But don't you, like from that subgraph, isn't the maximum bipartite matching more than one edge? Or more than one door? Or is that incorrect?
So I was saying from the first door we can't go anywhere else.
Yes, to say you can't unlock the first door, the graph would still say I can unlock 2 doors, I can match two locked doors to keys. So it would say 2's the answer, but like.
Oh yeah, so yeah, we don't find the maximum matching. The maximum matching isn't the answer to the problem.
Right.
The answer is the maximum subset, which is a prefix of these nodes,
Okay.
such that the maximum matching is the size of this prefix.
So you do the maximum matching on prefixes until you get one that you can't do.
Yep.
One minus that is the answer.
Yeah. Exactly. Cool.
Okay.
Very inefficient solution, but it works within the bounds, so I just didn't want to overcomplicate it. So our n is within 100, so there's, how should I draw this? Okay, we have Mary and Marty, and they have to this is the number of sushi that Mary can possibly eat, and this is the amount of sushi that Marty can possibly eat. Okay. And out of each sushi platter, so we have a bunch of different platters of some amount. So this is like M1, M2, M3, M4, and we have n of these. Now out of each platter, Mary and Marty are going to split them equally. That's if they're even. If they're odd, that means Mary or Marty can take one extra, since we're splitting them approximately in half. And we need to see, after splitting all of these approximately equally, if Mary or Marty can satisfy both of these conditions. So one way you could do it is basically to brute force it. So if we consider what are the possible amounts of sushi that Mary and Marty can eat. So let's say we want to give all of the extra pieces, let's say all of these are odd. We're going to give all the extra pieces to Marty so that Marty has the maximum number of sushi he can get, and Mary has the minimum number of sushi she can get. So we're gonna, every time we get an even, we're just gonna split them equally. Every time we get an odd, we're gonna split them equally, except Marty gets one extra. So we have like 4, 5, 8, 7. So out of these, so out of the first one, Mary will get 2, Marty will get 2. Out of the second one, Mary will get 4, Marty will get 5. Out of the first 2, sorry. Out of the first 3, we have to split this equally, so they'll each get 4 extra. So this is 9, and this is 8. and out of the last one, Marty will give Marty the extra one again. So Marty will get 4, so he gets 13, and Mary will get... what was that? 11? Okay, oops, yeah. So this is the most that Marty can possibly get, and this is the minimum that Mary can get. And you can see that they're like, we haven't lost generality, so like, we could have given Mary the extra as well. And now if we, if this doesn't fit our bounds, what we can do is we can just go, we can give one of the pieces that we gave to Marty to Mary instead. So we're going to minus 1 from this, it's going to be 12, and we're going to add 1 to here. So this is 12. And then we can check if this fits the bounds as well. And what you end up getting is a bunch of like pairs. So this is one of the pairs how we can split the sushi. And then we can give Mary 1 extra and Marty 1 less. And we can keep going until it goes back to the original, basically. And so this is a pretty inefficient solution. We're basically brute forcing every possible way we can split this sushi to see if it fits the bounds of Mary and Marty's like bounds that we have. And since the bounds were like n is like the number of sushi is less than 100, and each of these sushi is only up to 1,000, what we get is pretty much like a time complexity of O and M, which was 100,000, which works in this bound, these bounds. I'm sure there's like a faster solution. Does anyone have a faster solution? Otherwise, I guess you could have just brute forced this. This.
I kind of thought about it as in the minimum Marty and Mary had to have, and then spare, which could be distributed any way you want.
Oh yeah, okay.
And so you want 0 spare, so you like +1 to Mary if you think it should go to Mary, or +1 to Marty.
Yeah. Since there were like 2 bounds here, I wasn't sure how exactly to assign them.
Oh, okay.
Yeah. Is there like a way?
I was doing a thing where if Mary currently has less than x1, you +1 until you have more than x1. And then the same for Marty if he has less than x2.
Oh, right, okay.
It's also kind of inefficient. I think it's still O of NM, but it's just another way of thinking about it.
Yeah. That's also a different way. So you could start off with, let's draw this here. Start off with like 11, and then there's 2 extra. Yeah. And then you assign them and see if they work. Yeah. I didn't see a different way of doing like basically checking every single possible solution. And yeah, I guess this would be nice. Cool. Shall I move on to any other problems that anyone needs? Any? Up to 200 cities. Each of these cities have some amount of neighbors, which can be either 2 neighbors, 3 neighbors, or 4 neighbors. So we know from the question that 2 neighbors corresponds to a corner. So like the cities will be arranged into a rectangle. So the 2 will be a corner piece, a corner house. 3 will be an edge house, so somewhere along the edge, and 4 will be somewhere in the middle, so somewhere like here. We also know that the dimensions of the rectangle is at least 2, so we won't get like a row of houses. So we know that there must be like 2, 3, and 4. So first of all, overall we need to assign all these houses into like a valid configuration. And if there's no valid configuration, then we print -1. So first of all, we can look at the corners. Now since it's a rectangle, there needs to be 4 houses for the corners. And we can, if we're like, so if we have a map that we're trying to assign it to, we can basically pick one of the corners and put it in the top left. And we know the IDs of the neighbors of the houses. So we know that one of their neighbors has to go here, and one of the neighbors has to go here. And basically, we we can basically pick one of these neighbors and assign it to an edge because we don't know the dimensions yet of the entire rectangle. So we can pick this, let's just pick one of the random neighbors, one of the two neighbors that the corner house had. And this house will have three neighbors. So one of them we've already assigned, which was the corner piece at the top. One of them is this house right here. And this will have three neighbors. So we know it has to be like a middle piece. Oh, sorry, this will have four. So it has to be like one of the things in the middle. And then we'll have another neighbor with three. So this neighbor will have three neighbors itself. So now we know what the next edge piece will be. And we're going to do the same process on here. And we get the next neighboring house with three, and that'll be our next edge. And we can keep going until we get to the edge, and we'll know it's the edge when this neighbor has two pieces, two neighbors itself, which means it's a corner piece, which means we've reached the end of this first column. And we're going to do the same thing with each of the next columns. So now we knew that this house had another neighbor here. So we're going to check that. We're going to find this middle piece. And at each of these steps, we've got to make sure that all of this is valid. So this house has to be the neighbor of this house and this house. Otherwise, it just doesn't work. So we can print -1. We can just exit the program. Otherwise, we can just keep going down this column, assigning each of these. And we end up with the end of this, which should line up with the neighbor of this corner. And then we can keep going on the next column. And we're just going to keep going down like this until we get to the end of the rectangle, which should mean that all of the house IDs are assigned, and we should end up with a valid configuration. Otherwise, it's invalid. We can print -. So that was one of the ways to do it. And this was mostly like implementation details. There's also different implementations that you could have used. So this was one that I found. Okay. So, have any other questions?